Hello guys, good morning and welcome back to our class here in ESci132, your mechanics of deformable bodies. And yay, your Christmas break is fast approaching. And what are your plans for Christmas? Do you have any plans, or are you excited of taking a break from all of these stresses that we have right now? So it's up to you. Pero, yeah, let's finish our topic first before we'll go to our Christmas break. Sure. So, we are now done on our third module. Our third module talks about axial loads, and we already knew how to solve for the forces, the internal forces in an axially loaded member, and we also knew statically indeterminate axially loaded members, and also thermal stresses. Okay, and on our next module, on our fourth module, we will now be talking about torsion. So as you can remember, torsion is a moment that is exerted along the longitudinal axis of a shaft, perhaps. So specifically for this lesson, we will talk about the torsional deformation of a circular shaft. And later on, we will generate an equation for us to be able to solve for the deformation of a material due to torsion. And we will learn torsion formula. Okay? Our goal for this morning is that first is we need to understand how the deformation of a material due to torsion works. And number two is that you should be able to generate a formula that will show the shear stress of a torque-loaded member. And number three is that you should be able to solve for these kinds of problems, especially for these shear stresses for shafts that are subjected to torque. Okay? Again and again, torque is a moment that tends to twist a member about its longitudinal axis. Okay? So, this one is more applicable to our machines, since our machines have this what you call shafts. And in order for the mechanical parts of that machine to work, then these shafts should be able to rotate, because that is the means of transmitting power from your engine to your machine in order for it to work. So therefore, designing your shaft is very important, is very critical in making a machine. So I think you are very familiar on how a material will deform when it is subjected to torque. Diba? We all knew that when a material, so let's say we have a circular rubber material. Okay, this one is made of rubber. And we are putting guidelines in this rubber. Okay, nagbutan lang tag mga line-line para makibautas sa behavior sa deformation. Okay, so if this end, at the rear part of this kuan, of this shaft is fixed on a wall, so kanina fixed ni siya sa wall, fixed sa wall. Ani. And then, this part right here, na ay gi-apply nga torque. What will happen to our material? So again, the rear end of this shaft is fixed on a wall, and the front end on this shaft is subjected to a torque. So what will happen to your material when it deforms? Well, obviously, it will look like this. So this material will deform like this. Okay, when you apply a torque going, what kind of direction is this one? Counterclockwise direction. So it will look like this. So as you can observe, this lines right here still remains the same. It didn't change in position or whatever. But as you can observe, these longitudinal lines, they, instead of having it horizontally, then nagslant sila may. And if we're going to look at it here on this this section here, mabantayan mo na siya change in angle dira. Okay? And also take note, the shape of the cross-section didn't change. Morning atong circles right here. And ang imo lang jud longitudinal lines ang nag-twist. And your radial lines, which are this one, they remain straight. But instead of having it on an initial position of dire, ni tuyok siya into that direction. So therefore, there is an angle of twist nga nahitabo diri sa atong isa ka end. And that is what we need later on sa atong topic. Okay. So sige daw, ato daw ni observe. So ato ni observe nga phenomenon. Okay, let's observe again this shaft. Katong rubber na to nga shaft kaganiha. And again, the other end, the rear end is fixed on a wall and the front end is subjected to a torsion, to a torque. Okay? So, what will happen? So, observe this line right here. So, this is your radial line. Ang kaning imong radial line, it extends from the center of this circle into the outermost part of this circle. And then, ato na siya gi-extend from the front to the back. So, mao ni siya. Okay. And what will happen? So, this is your initial nga position sa imong mga radial lines before nimo gibutangan og torque. But, what will happen if we are going to twist this one? Padong dere, ato ikuan pa ngana. So ang mahitabo, since this one is fixed on the wall, it will still remain at this position. But on the front end of this one, ang mahitabo, mo rotate siya at this position siguro. And then moingana siya. So what happened? So there is a change in angle right there. So this is the initial position of your radial line before your torque is added. But later on, after you have applied a torque in this end, then it rotated at a certain angle, and that angle is what you call your phi. So this is your phi. And ang atong phi, ang kadakon sa atong phi will depend kung asa na siya no-locate diri sa atong material. If it is located here, diri kung tahay nga part diri, then you will observe that your phi is smaller compared sa atong phi sa gawas. Okay? And kung diri ang imong kuan, kung diri ang imong phi, then your phi is 0. So, maximum ang phi kung nasa sa pinaka-layo nga part sa imong deformation or kung asa nag-i-apply ang imong load. And then, nagtikagamay siya until kung muadto ka dito sa atong gi-attach sa wall, then mo 0 na ang atong phi dira. Okay? So, sige, let's study this portion right here. Ito ni kuhaon nga plate. And this one is located X away from the rear end. Okay. So, ato, magkuha ako ani nga plato ha. So, ato na i-zoom nga plate. Okay. So, again, this is your circular element. Ang kani nga element, and kana siya nga element is from a distance of X from the rear. Okay? And again, kung magkuha ka og differential element sa imong material, always, ang thickness ana niya is dx. Okay? So, nagkuha ko plate again, and then ang thickness atong plate is dx. And this is the center of our plate. And given the radius daw from the center to the outermost part is, let's call C. Okay? And we are taking an element na pod, a small element from this material. So nagkata na nga element. Okay? And kana nga element, so mo ni ang initial position sa atong element before siya ni deform. But later, after sa deformation, what will happen to your element? It will rotate. Gikan sa iyang likod, ni-rotate siya pa daw sa iyang atubangan. And naingani na siya. As what is illustrated diri sa atong kuan kaganiha. And tungod ana, then imong radial line diha sa kuan, it will also extend. Okay? So mo ni nahitabo. This is what happens to your element after the deformation. Ang nahitabo ana sa imong side view, naingana na siya. Okay? Which is initially ng ana siya. Initial nya final. Which is ang final mao ni siya ha. Ang initial mao tong kaganiha. Nga undeformed siya. And then there are two angles right here that you should observe. So as you can recall dito sa inyong shear stress nga lesson, iba initially when your material is a rectangle and it is subjected to a shear stress, perhaps paingana ang direction sa iyang shear stress, then it will deform like this. So asa ra gani ang atong shear strain dire? Ang atong shear strain is located diha. Mo ni atong gamma. So this, at the same time, this is also your shear strain. And since this one is located on the outermost part of this cross-section, then this is your maximum shear strain. Ganong naman tayo maximum o naman tayo minimum. Then probably ang atong minimum shear strain is located at the center of this cross-section. Because as you can observe, ang kaning atong deformation due to your shear stress will depend along the radial distance from the center of this material, of this element. So, sige, ato i-observe diri sa pinakatunga sa atong element. Di ba, gamay kayang iyang kuan. So, probably, diha sa tunga, ingana na siya. Mo ni ang sa center. Imagine ha, nga ato gistorya kay kanang rectangle nga naa diha sa atong kuan nga ni ka thickness, so man ni atong dx nga na. So ingana na siya sa center, and then diri sa tunga probably nagtikadako na siya sa morning point B, morning point A, unya morning point C. So point B nya sa kina gawasan, then dako na kaayang iyang deformation. This is point C. So manang giingon niya nga gamma max ni siya. Okay? Ang kani siguro gamma lang. And then kani probably 0 because it is located at the center. So mo depende ang kaning imong gamma kung asa siya na-locate gikan sa outermost padung sa innermost. So kung nasa sa innermost diri, nasa diri sa tunga, then 0 ang iyang shear strain. Pero kung nagtikagawa siya padung siya diri sa atong kuan outermost, then gradually pod ni increase pod ang iyang shear strain until it reaches to the outermost part, which is your maximum shear strain na diha sa atong material. Okay, understood? So mo ana siya. Sige. So let's say instead of having a rectangle diha sa atong pinakagawas, nana pud tay ibutang another rectangle diri sa atong sulod. Lisod man siya i-drawing, guys. Kay ba ko, guys, nga lisod siya i-imagine sa drawing. So much better siguro if you should read on the reference that I've gave you. Okay, so diha tas tunga na pod. Wala ko kasabot sa akong drawing pod noon. Okay. Mo ni sa atong point B. Okay? And kanang atong point B, let's say it is from a distance of rho. Okay? So ang distance sa atong element B padung sa tunga is rho. On the other hand, ang distance sa atong outermost part aning atong plate padong sa tunga is your C. Okay? So, rho ang distance again, gikan sa atong element at a certain distance from your center, rho. Okay? And your shear strain diha dapit sa imong rho is your gamma, which is mo ni shear strain. O para sa gapon na siya nga application diri ha, ikan sa pika side padong sa diri, mo ng angle. And then kani nga angle diri, this is what you call your d phi. Mo na ang imong differential nga angle of twist. Okay? Along this element, this plate element. Okay. So, padayon ta. Naglibog na pa mo, na-stress na mo. Yes, ako po, na-stress ko sa pag-explain ninyo kay libog kay i-draw. Okay? Pero nakasabot ko sa gitodlo ha, pero wa ko sabot sa pag-explain. Okay, sige. Ato i-drawing ni Usobe para mas klaro. Ato itana sa front view. Ang kaning nahitabo diri sa atong row. Front view ni ha. Front view. Okay. So morning ito nga sa atong kuan element, morning atong radial line. Then morning ang atong element at point B. Okay? But after the deformation, ang nahitabo ni change siya og angle. And kani nga angle, maning imong gitawag nga d phi. Okay? Kana siya. And then, di ba kay initially mao ni ang imong rectangular element, pero final na siya diri na locate. So, nag-change ang iyang kuan. Ato na tanawon sa top view. Top view. Ang nahitabo sa top view, di ba kay plate man ni siya. And then mao ni ang iyang dx, mao ni ang thickness. So, mao ning atong kani nga line nga gi-extend ato na pud ni gi-extend padong sa likod mao na siya. Pero tungod sa deformation ni ingana na siya angle. Okay. So, this is your differential element before sa deformation. So, ingana na tong differential element ha. Ingana na to differential element dira. Masin maglibog mo nganong rectangle siya diri, rectangle siya diri. Kay ani ang iyang itsura sa differential element. So, unya ang thickness ani mao ning dx. Okay? Which is kani. Okay. But after the deformation, ang nahitabo sa imong rectangular nga element, naingana siya. And then, morning atong gipakita, kani. Okay? And this angle right here is now your gamma. Okay? Monang gamma. And then, the location from here to here is your rho. Okay? And your angle right here is your d phi. Okay, kagets na? Sige. So, mo na akong gi-draw diri. Libog kayo siya i-draw kay 3D man, libog man jud na tanawon kung 3D. So, mo to siya. Nag-lecture pa lang taas na kaayo. Okay. So, mo na siya. Now, asa man na-relate na ang imong kaning d phi og ang imong gamma. How can your d phi and your gamma be related? Again, your gamma is your shear strain diri, mao na siya, and your d phi is your angle of twist, mao na siya. So how can they be related? Di ba? Naa sila'y same nga location diri, naa sila'y similarity diri. Ang sa may lang similarity, ang kani is 1. And at the same time, dito sa atong element sa B, this one. That is your arc length. Diba? Ang imong kani nga triangle ug ang kani nga triangle, ang ilang common is ang kaning arc length dira. So, pwede na nato magamit in order for us to equate the relationship between your shear strain and your angle of twist. So how can they be related since equal man sila og arc length? Let's say ang arc ato itawag kung dahil ang arc length is R. Arc length ni ha. Arc length. Your arc length is equal to unsa man na? Radians times the radius para makuha ang arc length. So, diri ta una sa kaning dako nga triangle. Diri lang sa kaning atong element nga gamay diri. Kani. So unsa man na? To get your R, arc length sa aning gamay, unsa man? Rho times your angle which is d phi. Okay? So rho times your angle in radians. And also at the same time, it is equal to diri na punta sa kaning atong isa ka triangle which is naa na po diri sa atong B. dx times, so which is kani ato tanawon be. So take note ha ing ani. Same sila og arc length. Ang arc length mo ni siya. Mo ni siya nga arc length, muning R, and mao pod ning arc length niya diri. Mo ni atong gipangita. Okay? And for you to be able to get your R, which is this one, sa diri, sa front view, rho times your d phi. Okay? Para makuha ni siya. And di ba kay same raman ni siya og kani? So therefore, diri na pud sa atong isa, dx, which is this one, dx times your gamma. Okay? So therefore, pwede din na nimo siya ma-equate ang imong kani silang duha as rho d phi is equal to gamma dx. And ultimately, you will have this equation. Gamma is equal to rho d phi over dx. Okay? And if we are going to manipulate this equation, we can have gamma over rho is equal to d phi over dx. In kanang imong gamma over rho, mao man na siya sa imong b, di ba? And since your d phi and your dx is constant throughout, di ba ang d phi kay di man siya mag-change bisag asa ka na-locate gikan sa innermost padong sa outermost, di siya mag-change ang imong d phi. And also ang imong dx dili siya mag-change gikan sa sulod or any parts of this element. So therefore, you can also change this one instead of having gamma over rho lang. Kung nasa sa pinaka-outermost, you can equate it into gamma max over C is equal to gamma over rho. Okay? So, still, these two are the same. And therefore, we can also arrive on an equation by substituting this one, since this one is equal to this one, then you will have this equation. Gamma is equal to rho times gamma max over C. Okay? So, this one is your equation that will relate sa imong radius or sa imong location sa imong element from the center to the outermost part and for your shear strain. Okay? So, libog siya, no? It's so libog. I understand you. Okay. Samot na nako kay libog siya itudlo. So, kamo ang gitudloan og libog, nalibog pod mo. Pero, nag-generate lang tag equation out from this concept we have right here. And we arrived in this equation. And this equation will be applied later on as we are going to generate a formula, and that is what you call your torsion formula. Okay. So, kaning atong torsion formula, it will relate sa imong shear stress and your torque applied. Okay? So, unsa man na siya? When an external torque is applied to a shaft, then it will also generate a corresponding internal torque within the shaft. Okay? And we will develop an equation in this segment right here for us to relate this internal torque and the shear stress distribution of your shaft. Okay, so again, let's imagine that our material is behaving linearly elastic. So therefore, when you say linearly elastic, kung dako ang stress, there will also be a corresponding increase of your strain. And their relationship is linear. So therefore, so as you can remember on our equation kaganiha, you have your gamma is equal to rho over C times your gamma max. And again, if we are dealing with linearly elastic materials, then we can just simply change this shear strain here into your shear stress. So we can also apply this one. Okay? So, unsay pasabot ana? So, for example, we have again that cross-section. Front view lang ta. And then, maoni ang imong initial nga position sa imong radial line before the deformation. But after you have applied a torque, then it rotated right there. Okay? And you have this differential element right here. Okay? And your element will obviously be at its maximum again, maximum nga strain kung nasa sa outermost part. Pero kung nasa sa sulod-sulod gamay, then nagtikagamay ang imong strain, then hangtod nakasatunga ni zero ang iyang strain. So therefore, this is your gamma max again. And since this one is linearly elastic, then we can say that this is also your tau max. Kung asa ang pinakadako nga strain, dito po ang pinakadako nga stress. So kung asa po dapit ang zero ang strain, then of course wala po na siya stress dira. Okay? So ang kani sigurong location mo imong gitawag nga gamma and then your tau. Okay? So mo lang na ang atong pasabot ana. So therefore, we can just use these two equations interchangeably depending on unsay imong gikailangan. Okay? And so let's call this one as your differential area, your dA. And di ba, as you can remember, unsa gani formula sa atong shear strain, shear stress, di ba, nakinumdum ta, your shear stress is equal to your shear force over your area, dV over dA. Okay? So therefore, your dV is just equal to tau dA. Okay? So this is your differential force. And mao na ang formula sa imong differential force. But if you're looking for the torque, di ba nakibawta nga torque is the same sa imong moment nga, sa to? Force times distance. Ang force mao ning atong dV, and then ang distance mao ning distance from the center padong dito sa asa na nga differential area, which is kani. Okay? Mao na siya. And ang distance ato gitawag kaganiha nga rho, and let's still use your rho. So therefore, your dt, your differential torque, is just equal to your dV times your rho, which is, kung ato siya ibungkag, then this is rho times t, your tau dA. Okay? And since you learned that your tau is just equal to this one, then you can expand it further as rho times rho over C tau max dA. And simplifying it further, you will have rho squared over C tau max dA. And take note, these two are constant. Constant ang imong radius, di ba? Kay ang C kay ang distance from the center to the outermost part. Constant na siya. Ang tau max is your shear stress at the maximum of your cross-section. So, constant na sila. So, we can move that out. And then, ato ni-integrate. So, therefore, ang mahitabo is T is equal to tau max over C integral of rho squared dA. Okay? So, unsa naman ni siya? If you can observe this one, this is familiar sa inyong statics of rigid bodies. Kani nga form, kani nga forma, nakahinom ba mo sa atong statics sa una nga natay r squared dA, natay x squared dA siguro. Nakalimot na ko. Pero, as you can recall, this one is your moment of inertia. This is your moment of inertia nga formula. And this one is a special case because this one is a polar moment of inertia. Kaya nga naman, it is from your cross-section nga circle. Katong atong mga na-learn sa una, ito sila nga mga moment of inertia kay dito sa atong mga rectangular nga mga materials, nga beams, whatever. Okay? So therefore, we can simplify this one. This one is your J. And if you know the polar moment of inertia of a circular shaft, then you can simplify that one. And therefore, we can simplify this equation further to get your shear stress maximum. Imulang buhaton is your T multiplied by your radius over your polar moment of inertia. So, this is your torsion formula. Okay? So, maara na inyong i-memorize. Tapos kaya itong mga formula ganiha, maara na ini ang inyong i-timanan. Basta, importante, kibaw mo mag-char, kibaw mo mag-generate og formula, gikan sa ato na learn dito sa atong gipanghimo kaganiha. Okay? Understood? So, this is your general formula for your torsion. Your T is your torque. Your C is the outermost distance from the center, which is basically siguro your radius. And your J is your polar moment of inertia. Okay? Can you remember what is the formula of our polar moment of inertia? Your polar moment of inertia for a circular shaft is just equal to pi over 2c to the fourth. Okay? And this one is for your solid cross-section. And for your liquid, for your hollow cross-section, you have this one. Pi over 2 outer to the fourth power minus inner to the fourth power for your hollow kung tube. Okay? Ano lang? Yay! Nakahimo na to sa formula. Now we can have our example. Sige, let's have an example. Ato gi-change ang lighting kay nag one man unya murag gloomy atong weather, so dapat gloomy pud ang atong atong feeling karon. Okay, so in this first example, we have to compare two materials, two shafts. The first one is your solid shaft, and the second one is your hollow tube shaft. Okay? And ato daw i-compare ang kaning duha kung asa diri sa duha ang mas dako og mahandle nga torque before they will behave plastically, perhaps. Okay, so you have this 100 millimeter solid shaft, and you also have this hollow shaft, which is 100 millimeter pod ang iyang radius. Okay, so again, we are looking for the maximum torque that can be applied to this one before it behaves plastically. So, how are we going to solve this one? Can you hear me? Because it's raining, kusog ang uwan dere. So, anyways, first, we have to determine unsa nga formula atong kailangan. We need our formula, tau max is equal to Tc over J. We need this one because we are already given that the maximum allowable shear stress for the two materials is 75 megapascals. So that value we are going to use in this tau max right here. Okay? Because this is the maximum shear stress pod nga mahitabo diri sa imong material. Okay? Your T, mo na imong gipangita. Your C is obviously your the outermost radius of your material, and your J is the polar moment of inertia. We already have this one. We already have this one. This is what we're looking for, and we don't know our J. But our J is solvable. So let us first solve for the polar moment of inertias. Okay. Ato unahon na sa solid. J solid is equal to, unsa to? Pi over 2 C to the 4th. Sakto? So, unsa man ni siya? Pi over 2 times 100 millimeters. But, okay, let's make it meters. So, 0.1 meters to the 4th power. And that is equal to 0.1571 times 10 to the negative 3 meters to the 4th power. This is the moment of inertia of your solid shaft. For your hollow shaft, pi over 2 minus C outer, which is 0.1 meters to the 4 minus 0.075 meters to the 4. And that is equal to 0.1074 times 10 to the power of negative 3 meters to the 4. And now, we can now solve for the maximum shear stress that your solid and your hollow tube shaft can handle. Okay, so for solid shaft. Okay. So for your torque sa imong solid is equal to J tau max solid over C, which is money 0.1571 times 10 to the power of negative 3 meters to the 4th. And then your maximum shear stress, allowable shear stress, that is 75 megapascals. Unsa man na, dapat ato siya himong newton per meter. So that is 75 times 10 to the power of 6 newton per meter. Right? Divided by your C. Unsa imong C? 0.1 meter. So therefore, your maximum torque that can be applied sa imong solid shaft is 118 kilonewton meter. Okay? So, you can apply up to 118 kilonewton meter nga torque sa imong solid shaft before it will reach to its yield stress. Okay? Take note. Next. How about for our hollow shaft? So, na-erase ha? For hollow shaft. TH is equal to J times tau max hollow over C. This is equal to your J sa imong hollow is 0.1074 times 10 to the power of negative 3 meters to the 4th times your J, which is, your tau max, which is 75 times 10 to the power of 6 newton per meter squared over your C. Obviously, still ang 100 gyapon imong gamiton, which is ngano ang 100 man gyapon gamiton kay mao man ni siya ang maximum. Diha nimo malocate ang maximum nga shear stress. Pero kung kani ang imong ganahan pangitaon, then 75 ay imong butang. Pero dire man ta sa pinakagawas sa 100 gyapon, 0.1 meters. So therefore, your maximum torque is 80.5 kilonewtons meter. Okay. So these are your answers. So as you can see, your solid shaft can handle greater torque compared sa imong hollow shaft, which is very obvious kay mas dakog area na cover sa imong solid shaft compared sa imong hollow. Okay? And also, it is indicated sa itong problem, we are asked for the stress right here. The stress right here sa atong kuan. So, this is your TS. Muna mong TS, muna mong TH. And then we are also asked for the stress diri nga portion. How can we solve that one? So, ato ta. Balik tayo nga formula. And we are going to use the torque nga T with this value, 80.5. Okay? So, but dili na siya max because this is not the maximum na. Tau C lang ang tawag diri kay mo may pangan dito. Tau C is equal to 80.5 kilonewton meter times, and kani instead of C mahimo na siyang rho. Diba kay ang C mo man ni siyang outermost, pero ang kanang rho mo ni siyang distance from here to there, which is 0.75 meter. Oh no, 0.075 meters over your polar moment of inertia of 0.1074 times 10 to the power of 3. And your stress at C at this point is 56.2 megapascals. And these are your answers for number 1. Okay? Sayon ra no? Taas kaya ang atong introduction, pero sayon ra kayo i-solve ang atong mga problems. Another, we'll have 3 examples para makuan mo. Mahasa mo, char. Mahasa. Okay. So for our second example, we have this shaft that is supported by 2 bearings, and kaning shaft pod na ay tulo ka torque nga gi-apply dire. Okay. And we have to determine the shear stress at points A and B of this material. So kaning points A and B, gi-zoom in ang atong cross-section sa atong shaft at section AA, and mo na ang atong A and B. We have to determine the shear stresses at those points. So unsa amay nato pagbuhat? So first, we have to determine the torque at section AA. And how can we determine the torque at section AA? Well, we have to make a diagram. Diba? Mo ni ang atong first nga torque, and then second nga torque, and then third nga torque. This is 42.5 kip inch. This is 30, and this is 12.5. Okay. This one rotates counterclockwise. This one rotates clockwise, and this one rotates clockwise. So ito siya i-graph. So ato ingon nga ang counterclockwise ang pasaka, ang counterclockwise pa ubos. So 42.5 na ay torque na 42.5, so nisaka siya 42.5. So walay torque diri nga gi-apply, so consistent nga 42.5. Niabot og 30 clockwise, so ninaog 42.5 minus 30 nahimo siyang 12.5, and then 12.5 na po na nadira, and then nag-add na po kag 12.5 pa counterclock ay pa clockwise, so ni 0. And this is your section AA. So therefore, your torque at A is equal to 12.5 kip inch. Okay? Ano lang. Sige. So now, unsa kaya ito formula? T tau max is equal to TC over J. So we already have our torque, we knew our C, or we knew our rho, which is given there. Kaya diba, pwede ni siya nga tau is equal to T rho over J. Ay mo kalibog ana. Ang imong rho pasabot lang ana kay kung dili sa outermost part sa imong circle. For example, mo ni imong cross section, mao ni ang imong element nga gi-consider, then ang rho is the distance from there to there. Pero kung ang imong element is located on the outermost part, then this is your C. Okay? Mao lang na, lahi lang na sila. And then kung imong gitan-aw ang shear stress sa element, then mao nang atong tau max sa pinakagawas. Pero kung nana siya sa sulod, ato lang na siya gitawag as tau. So, they are the same equation, pero mao lagi ito, outermost unya nasa sulod, and then outermost nasa sulod. Okay? Ayaw mo kalibugan na, ha? Sige, let's proceed. So, we still don't know our J. So, we have to look for our J. Polar moment of inertia is equal to pi over 2 times C to the 4. And then, this one is equal to pi over 2 times 0.75 inch, which is equal to 0.497 inches to the 4th power. Okay, so now we can solve for stress at A. Okay. Okay, diba? Ang atong A is the outermost part, so that is your T max. Tau max is equal to, sa ganitong kuan, 12.5 kilopounds inch times your C, which is 0.75 inches, over your J, which is 0.497 inches to the 4. So, ang mong ipangita is kip kilopounds per inch squared, which is the unit of stress. And that is your 18.9 kilopounds per square inch. So that is your tau max or your TA. Okay? And now for your B, tau B is equal to 12.5 times kani atong C, instead of C, rho na ni siya. Unsay distance sa element sa B padong sa center? 0.15 inch over 0.497 inch to the 4. So therefore your tau B is equal to 3.77 KSI. Okay? So yun. Nga to lang kadali i-solve ang kaninga problem. I hope you understood this concept on how to apply this equation, because this is very important as we proceed to the next topics. Okay. For our last example, we have this pipe daw nga gi-subject siya og torque. Okay? Ang end A is supported against the wall, and ang sa pikas na wrench. Ang kaning wrench gi-applyan siya og couple. Okay? So we have to determine the shear stress at C. Okay? At the inner and outer walls of the central portion of the pipe, which is at point C. Okay. Saan na gani ni? Adi din ni couple, oy, sorry. So this is your wrench. Manay center, na-apply nga 80 newtons dire, then na-apply dire nga 80 newtons. And 200, 300. And to get for the torque, di ba kay diri man atong gi-focus kay diri man ta nangita sa section. So ato sa pangitaon ang torque at this portion right there. Tama na. Torque is just equal to the summation of moments. Summation of moments at point B going clockwise is equal to 80 times 200 plus 80 times 300. So therefore, your torque is just equal to 40 Newton per meter. Okay, so that is your torque. And basically, this is the internal torque of the hollow tube shaft. Okay? So ito ta sa atong tube. It is given that the inner radius is 40 millimeters and the outer radius is 50 millimeters. Okay. And what we're looking for is the tau, which is equal to T rho over J. Or TC over J tau max. Okay. And kailangan sa mangita sa polar moment of inertia, which is pi over 2, outer radius, which is 0.05, fourth minus 0.04 fourth. And this is equal to 5.796 times 10 to the power of negative 6 meters to the fourth. Okay? Now proceed. You can solve for the outer shear stress, which is kani, and the inner shear stress, which is kani. So una ta sa outer shear stress, which is 40 Newton meter times your C, which is 0.05 meter over 5.796 times 10 to the power of negative 6 meters. So meters, so Newton per meter to the fourth squared. And the answer is 0.345 megapascals. And that is your shear stress on the outer part of the tube shaft. And for the inner part of the tube shaft, that is 40 Newton meter multiplied by 0.04 meters divided by 5.796 times 10 to the power of negative 6 meters to the 4. And your inner shear stress is equal to 0.276 megapascals. So these are your answers. Taas kayo ito discussion, sayon kayo ito solution. Okay, so this is your torsion formula. And by the help of your torsion formula, then you have related the shear stress and your torque. The applied torque to your shear stress. And that is very important for you, especially as you're going to solve problems like this. So as a summary for this lesson, then you already knew what are torque-loaded members and say relationships sa shear stress o sa shear strain and whatever chuchu. We also have generated the torsion formula, which is your tau max is equal to TC over J, or your tau is equal to T rho over J. And then lastly, you have able to solve problems in relation to your torque and your shear stresses. So maula sa to atong lesson karon nga week because that is so very long, and let's continue the next topic on the next week, and that will be our last topic for this year. Dili school year, but for the year 2020. Okay, so stay tuned and see you again on the next week. Bye!